Okay, so the question is, if all else stays the same, that is the rate, the amount of time, the principal amount, and we only change n, what happens? If you break up your interest rate and you apply it a bunch more times per year, let's say every day or every hour, what happens? Does this amount just go and get bigger and bigger and bigger? Okay, well, let's take a look. So what we're going to do is that stays the same, 3 stays the same, the rate stays the same, the 1 plus stays the same, everything stays the same except the 12. So I'm going to use, anytime I get a chance to use Excel formula, I'm going to do that. So let's see, in Excel, in my formula, it's 1,000 times 1 plus 0.05, and I call this cell. So that's just the 12. I'm just calling the n, and it's going to spit out a number. Let's see how close we were. 1161.47. 1161. Oh, I got a small error here. We didn't invest 10,000. We invested 1,000. So I got a decimal error here. I wonder if you caught that in the last video. 1,161.47, which is verified by Excel. Okay, so now what I want to do is I'm going to let n be 12, do the same calculation. We're going to let Excel do the math for me instead of my calculator. Okay, so we did it twice a month. That's 24. Let's do it 3 times a month. N equals 36. Run that into my formula, and I got a little more money, but not that much. You'll notice what's going on here. Let's do it every day. 365. The interest is applied daily. Let's see how much money I have now. 1161.82. I only have like 40 more cents than if the interest is applied monthly than if it's applied every day. All right, so there's some kind of limiting factor here. You're going to study this when you get to calculus. But what's going on here is n goes to infinity. This amount does not go to infinity. It doesn't get bigger and bigger and bigger. There's a restriction there, and we can define that restriction or define that limit with a very special number called e. Okay, so what I'm doing here is I'm leaving this the same. I'm leaving the rate the same. N is the only thing that's changing. I'm leaving t the same. So here's my first ever definition of e, or one way to define it. As n goes to infinity, this number actually becomes e, and I'll show you that I get the same amount if I replace it. Then the 1 plus the rate over n to the n becomes e to the n. Okay? This number is showing up naturally. All right? It's just as I let n get really, really, really big, it goes to some constant base, and it's e to the n. So let me show you, so you believe me, that this is, let's use Excel. If I go equals, so same amount, 1,000, and I have this new base, exp, or e, in Excel it's exp, 0.05 times 3, which is what's seemingly a completely different formula, and I get this number, the same number I have here. Okay, it's just rounded a little bit more. So that means that I have a new formula, and we called it compounding continuously. The idea here as n gets really big is that you're compounding continuously. So as n goes to infinity, my formula, principal 1 plus r over n to the nt, becomes a new formula, e, sorry, that should be r, not n, e to the rt. Okay, that is, think about it as it's compounded every second of every day, compound continuously. All right, and that's the first time we see in this class where that number e shows up. So this is called compounded continuously. It's very useful model, and we're going to use e all the time now. And e, if you plug it into your calculator, e to the first, it's about 2.718. Okay, very famous number in mathematics. We're going to see it all the time. And when you get to calculus, you'll see it all the time. Okay, so this is compounded n times a year, n times per year. Okay, so you'll have these two formulas now for this application of exponential growth. You can read through this. Here's another way to define it. It's about 2.718. And then you'll have to be able to work with that formula as well. Very common for modeling money growth, anything that grows exponentially. Here's another example. Population growth in biology when resources are abundant and growth is unchecked. That means you have exponential growth, right? Just like those functions we looked at before, it grows very quickly. If that's the case, the population size over time can be modeled with that same model as compound interest compounded continuously. Okay, so hopefully that makes sense. The problems are pretty easy when you do them. You just have to, anytime you're given a formula, you just got to plug stuff in, and it's pretty straightforward. So let's do this one. You have a colony start with 1,000 bacteria. That's your initial amount. Growth rate of 2% per hour, so it's growing pretty quickly. Remember, 2% is a decimal, 0.02. And we want to know after 10 hours. In this case, time is given in hours. So we have our function 1,000 e to the RT, where t is in hours. And in this case, it's 1,000 e to the 0.02 times t. Run that through your calculator and get a result. And I get 1,221. Okay, now the real question comes, here's the real question, which we're going to study next. I want to know how long it takes till the bacteria gets to 10,000. Okay, so think about that for a second. How long before bacteria amount reaches 10,000? Okay, so you would say, well, wait a minute, that's the amount, that's the output. In this case, I give you the output instead of the input, and I set it equal to my function, and the question is find t, how long, so I have to solve this equation. All right, and I would say, well, I know my algebra, so the first thing I could do, I could divide both sides by 1,000. So that results in this equation, 10 equals e to the 0.02t. Now what do? This is new for us. We haven't done any of this yet. How do you get that exponent down? Or how do you solve for the variable where it's up in the exponent? And that's going to require logarithms. We're going to introduce logs in the next unit, next video. And you're going to be able to solve this using logarithms. That's the only way to do it. You might have done that before. You take the natural log of both sides. And we're going to spend some time on that. Okay, so summing up, we have our key features of the exponential models. It's either growing, it's in a B there, or it's decreasing. Applications, we saw our money application. We can talk about radioactive decay later. We'll do some more applications later, but it's very applicable. When you do your project for this course, you're going to do exponential functions because we can do a lot of basic modeling with exponential functions. Okay, next up is logarithms.